Okay, good afternoon. On behalf of IASTA, I welcome all who have gathered online and in person to attend inaugural lecture of IASTA monthly online lecture series. I am Manish Joshi, Secretary, Indian Aerosol Science and Technology Association. IASTA was founded in 1988 with an aim to promote, encourage, and develop the growth of aerosol science and technology disciplines and their applications in India. An important part of our mandate is to provide a platform for reporting and discussing new developments in aerosol science and technology and associated areas. For this, we conduct programs and activities, including IASTA conference in different parts of country. Our executive committee, under the guidance of Dr. S.N. Tripathi, who is the current president of IASTA, has planned to strengthen our role and conduct or provide support for various kind of activities useful for seasoned researchers, students, technocrats, and general public. One of these steps is the conduct of online lectures by well-known aerosol scientists and engineers on monthly basis. Now I request Dr. Neeraj Rastogi, who is Vice President IASTA, as well as who is the convener for this online monthly lecture series program, to tell you more in this direction. Dr. Neeraj, please.
Okay. Namaskar, everyone. First of all, thank you for joining us. So as Dr. Joshi has already indicated that we are planning to do multiple activities, and our purpose is to increase the interaction among all kind of researcher working in the field of aerosol, whether they belong to any field. So in this regard, I'm very happy to inform that IASTA has started a monthly lecture series, wherein every month we will be organizing an online lecture by eminent researcher, and this lecture will be about 45 to 60 minutes. And this will be given by many people working in the field of science or engineering or medicine, anything related to aerosols. This lecture will be followed by interactive question and answer session where one can directly interact with the speaker. The audience include, but not limited to, the scientist, academician, PhD and master student, postdocs, industries from India and abroad. These lectures will also be recorded and made available on IASTA YouTube channel. So in case if somebody missed some lectures, they can see it afterwards also. So on behalf of IASTA, I wish to request you all to take maximum benefit of this lecture series, interact with our eminent researchers of different fields, and direct interaction you can do. And in case if you are missing, you can always see this lecture on YouTube channel afterwards. With these few words, now I invite Professor Chandra Venkatraman to introduce our speaker of inaugural lecture. Dr. Chandra Venkatraman.
Thank you, Dr. Rastogi, for the synopsis about the lecture series and the new initiative. This evening, it's my privilege and great pleasure to introduce Dr. Mayya, and we are indeed fortunate that the inaugural lecture of our IASTA lecture series is being given by the eminent sort of founding aerosol scientist in India. Dr. Mayya has worked from the 1970s in aerosol theory related to nucleation, coagulation, charge-assisted coagulation, charge-assisted filtration, aerosol spray drying as applied to nuclear safety, as applied to air cleaning, as applied to nanoparticle synthesis, and many other fields. He superannuated from BARC after mentoring generations of aerosol scientists over there in 2013. And I was extremely keen that we should have a platform for Dr. Mayya to continue his work. And so we were very fortunate that IIT Bombay was able to bring him here as adjunct professor. As adjunct professor in the last 10 years, being associated with IIT Bombay in the Department of Chemical Engineering, Dr. Mayya continued his traditional work areas, but he has also broadly collaborated with chemical engineers who do not identify as aerosol scientists, but identify as fluid mechanics experts, as complex fluids related work. And he has done work related to charge droplet levitation, droplet breakup, fractal mobility, and various other topics. And of course, I'd like to say a couple of words on a personal note. I personally have interacted very extensively with Dr. Mayya from 1995. And very soon after I joined as a faculty in IIT Bombay, um, it became clear that, to get very, very good theoretical advice, uh, he was one of the people to go to, the BARC group. Of course, he himself has been working with his colleagues, Dr. Kotrappa, Dr. PVN Nair. He's been associated with KG Vora, with UC Mishra and others from the 1970s on to develop both aerosol theory as well as indigenous aerosol measurement and other instrumentation, which was a big focus. He's always been a very good examiner. He starts questioning a student at a low level of complexity, lets the student open up their entire understanding before raising the complexity level so that the student has a chance to demonstrate their entire understanding. So he was always a very good MTech examiner or PhD examiner for my students. In the last 10 years, we've collaborated on nanoparticle synthesis from nano droplet aerosol spray drying, as well as there's a course, aerosol technology, which I've had the great pleasure to have him collaborate with me on teaching various topics from the aerosol fundamentals, applications including aerosol instrumentation, uh, aerosol reactor engineering, nucleation, and different topics related to atmosphere and climate. So, Dr. Mayya, we are indeed fortunate, and I invite you to deliver your lecture today. Thank you.
Thank you, Dr. Chandra, for being very kind, saying very kind things about me. I have really enjoyed interacting with you. In fact, much of what I'm going to say today is in a way a reflection of the conversations I would have had, one with Dr. PVN Nair, interested in the history and the people of aerosol science, and secondly with Chandra herself, because we had innumerable conversations on the history, the pedigree, how the science came. And this is an opportunity given to me by IASTA for recalling or recounting the tale. So these are kind of this, I'm going to tell you a scientific tale of the subject perceived from my perspective. So at the outset, I thank IASTA Managing Committee, Dr. Rastogi, and other members, Dr. S.N. Tripathi, for giving me this opportunity. Perhaps my thinking over the past maybe 4 decades or so to share with students. So Dr. Chandra, Dr. Modak, Dr. Sahu, my colleagues from BRC, we will sort of have an exordium of this subject, and that is what I will recount. So let me can I move the next? Yeah. So this picture tells a tale. It was taken without in a spontaneous manner, without any archival intention. After all of us were strolling around after the IASTA 95 conference in Ahmedabad, when I looked back at this picture, it occurred to me that it's probably telling a tale of transition of aerosol science from a founder generation represented by Dr. P.V.N. Nair and perhaps Dr. Kazumi Nishioka to an emerging younger generation represented by Dr. Chandra Venkatraman and Dr. Balwinder Sapra. I will tell you about Dr. Nair a little later. Now, I must say that perhaps Chandra Venkatraman is the first chemical engineer to have come to India and pursued aerosol science and pollution studies from a very eminent group of Professor Friedlander from US. And as all of us know, today she is one of the leading scientists in this field, recognized all over the world. Dr. Sapra, she today heads almost the entire aerosol activity of Bhabha Atomic Research Center, apart from, of course, several other responsibilities. So there is a transition, and I stand as a transition generation person in this. And as a transition generation person, I sit before you to tell this tale. So when I joined Bhabha Atomic Research Center in the mid-70s, I was asked to work with one person called Dr. P. Kotrappa to work on aerosols. I was very disappointed because I wanted to work in theoretical physics. So Kotrappa was a very suave gentleman, although he's actually, I know he's a Kannada person, but he had an American sort of accent. So he told me in a very sophisticated way, aerosol is a brand new subject and there's a lot of theory in it. And young man, let me tell you, if you see one, you see all. I had never looked back since then and never had regretted my decision to have entered aerosol science. It's truly a beautiful subject, which if you see one, you will see all. However, in those days in 1970s, what did we see? There was very little to look around. When I joined, there was just one journal, Journal of Aerosol Science. There was one book, more or less, Mechanics of Aerosols, revered book by Revered Nikolai Fuchs. Kotrappa had a personal copy of that in the laboratory. He had a personal copy of T.T. Mercer. For practical aerosol scientists, T.T. Mercer was the book because many experimental methods he would suggest. That was it. And for a little high profile person, there was a book by Heidi and Brock series on physics of or dynamics of aerocolloidal systems. It's very fascinating. You will not understand much. I was interested in theory, so I used to often go and open the pages and learn from that series of articles. And of course, for those who wanted to publish more fundamental level, there was Journal of Colloid and Interface Science. Apart from this, we had, and of course, there is an old book lying in the shelf of library, Whitlaw Gray on smoke, which we opened occasionally, but it looked at an old book, already yellow pages. Apart from this, therefore, for meeting the rest of the knowledge, desire for knowledge or rest of your meal, you have to look around. So we had to read physical reviews, we had to read Industrial Hygiene Association Journal, Occupational Safety, Radiation Protection journals like Health Physics and Physical Chemistry if you're interested to look at that level where people published, and of course, Journal of Colloidal Interface Science. From that era, coming today, situation is very different. We have scores of books. Perhaps I've listed a few, like you have Friedlander's book, and you have Seinfeld and Brandeis, you have Plupacher and Klett. You have many new journals. Just I am only indicating aerosol science and technology, but there are many Asian journals today. So the situation has changed. So what is it? What is it that held us from that era to this era to this subject? So first, of course, is a very fundamental question we always rises in the mind. So what are we discussing? What is an aerosol? So it's a kind of Many definitions are meant for students, so we all teach aerosols is simple. A simple definition is a tiny collection of tiny particles or droplets suspended in air. It has very, say, trace kind of an amount, less than a ppm. It's important because of its consequences and applications, similar to colloids, hydrosols, suspension in liquid. And of course, Professor Friedlander, I think, had coined the word cosmosol, and to expand the definition of fine particles in science. So that was also taking grounds. And we know it's a discipline which focuses on aerosol science, therefore, is a discipline which focuses somewhat on fundamentals of how particles are formed, how they transport, how they interact, etc. And as Pratim, I heard it from Pratim, it's called an enabling discipline today that helps tackle global challenge problems related to energy, environment, health, medicine, and advanced materials. I would also mention about a thought-provoking definition I read in the book by W.H. Marlowe, Aerosol Microphysics. It's interesting because it gives a more fundamental structure for the subject. Aerosol is a two-phase system consisting of a host gas and a condensed phase in which the latter is a non-equilibrium system. This necessity of this definition comes from the fact that if you go by size alone, you will enter into a quandary that SO2 molecule and the radon decay products are the same size almost. So if you want to include radon decay products, which are solid atoms of solids and they have all properties of aerosols, then by size alone, you might have to include SO2 or even radon itself. Whereas the definition of being non-equilibrium is the key issue. A radon decay product can never be stabilized. It very quickly attaches. It has all the properties of an aerosol, but SO2 molecule being a trace gas is more or less stable. So this is the fundamental definition of an aerosol as opposed to trace gases on the one hand, and as opposed to large macro particles on the other, like grains of sand which fall within seconds, are too unstable to be called an aerosol. So we have therefore limited ourselves a range, of course, but also a consent. There is a question which comes to the mind, why aerosol science is a separate discipline? This is a question, it has a history. Some 2 decades ago, when as a secretary of Indian Aerosol Science and Technology Association, we approached Chairman ISRO for funding a conference in ISRO. He invited first me to make a presentation, and he invited Director Park also to be there. So I remember Dr. Bhattacharya also went to Trivandrum and I also went. And after going there, he asked me, look, Mayya, I have this question. Aerosol is one of the trace constituents of the atmosphere. There is oxides of sulfur, oxides of nitrogen, carbon monoxide, ozone, and then aerosols. But I have never heard of sulfur dioxide People's Association, carbon monoxide People's Association. Why do you need aerosol association? And then Director Bark also said, I too have the same question. So I was to defend it. And probably today what I'm going to talk is an expanded version of the defense I made. I was prepared for that answer, a question. It was hinted to me that he will ask that. So I had prepared in a way. And my fundamental defense is there are scores of disciplines to which aerosol applies, not just to atmosphere as you see it, not just as a pollutant. And there is an underlying commonality, like you have physics and chemistry, which govern an underlying commonality of so many phenomena, in fact, the whole world's phenomena. Similarly, aerosols science also covers an underlying principles behind a vast variety of subjects. And some of these are like natural phenomena, formation of clouds, color of the sky. So several early scientists worked on radiation transport, basically to understand the color of the sky, sunset, and then of course early electrical studies were not for air cleaners but for atmospheric electricity understanding. We have, of course, increasingly urban air quality issues, air pollution and visibility, human health issues now, increasingly because of the new form diseases, global burden of diseases and associated control technologies. Climate change, we know how important aerosols are in this, radiative forcing, weather patterns and rain patterns. Then synthesizing nanomaterials is the technology. As I mentioned, Friedlander calls them as good aerosols, which are useful, novel materials synthesized through aerosol route, then drug preparations and delivery. to name a few topics. So these are some of the founders. I'm going to go into a few other names, but this is a personal view. I view some of these as the modern day aerosol founders. So the messiahs of after 70s, I would say, like Nikolai Fuchs, the father figure. There is nothing in aerosols you can do without knowing. If you have not heard of Fuchs, it's better you hear of him to call yourself as an aerosol scientist. So that's the way we see it. It's called the Fuchs formula, without which you cannot do a calculation in aerosols. He established aerosol as a discipline. Then we had Sheldon Friedlander, of course. Professor Chandra will have tales and stories, very exciting stories about this person. We met him when we invited him to Aerosol conference in India in 2005. And the Aerosol conference was a success because he turned up. It was so important. We had the largest foreign delegation in India at that time on aerosols, just because so many companies came because Friedlander came. And it's because of the science he has done, the self-preserving theory, application of aerosol to industry via reactor engineering, aerosol reactor engineering, and then application of methods for pollution, statistics of pollution measurements like mass balance, chemical mass balance methods, etc. And he's founded aerosol technology as a sub-discipline. Then, of course, speaking from an Indian platform, it is Dr. K.G. Vora, with whom, although I never worked so-called under him, but he was always around. He was always an inspiring figure, always seen with a tie, very sophisticated, minimum talking person, very soft-mannered. He directed then radiological and environmental research in BARC, and his aerosol work maybe just about 20 to 30% of his responsibility was more of a radiation protection person. In fact, the entire radiation protection program of atomic energy was completely indigenous because of the efforts of people like Vora, developing phosphorus and all. So he's an Indian pioneer aerosol scientist, truly a founder of aerosol science in India. In fact, there was no word aerosol science in India before 1950s, and it was BARC, which is the founding place. There was no atmospheric studies, no pollution issues. It was all because of I will tell you the reason why BARC took it up. And he's also one of the founding members of the Journal of Aerosol Science with C.N. Davis, Norman Davis, and he worked on binary nucleation and atmospheric chemistry. We will come to him a little later. And I have this thought that any great science must have a great history, connection with human development of human thought. And it's quite incidental that I came across an issue of Varahamihira's work. It was actually pointed out in an article by P.C. Ray on ancient Indian science in Indian Chemical Society in 2011, where, of course, Dr. Ray dismissed Varahamihira's estimate of the size of an atom as off by a factor of 100 or so. So it was ended there. However, when I went back to the original translations and verses and then tried to see, I found that Varahamihira is actually sized up the aerosol particle. And I will tell you why. And about Varahamihira, we should know that he's one of the Navaratnas of Chandragupta, very well known on Indian mathematics. It's a big figure, very confident person, a multidimensional personality. He even wrote that almost I have done work on every area of human interest because he wrote compendiums and compendiums on many topics. So his Pancha Siddhantika is very famous. It's a compilation of Greek, Roman, and Indian astronomy. And he's the first one to start the culture of literature, exhaustive literature survey. So he analyzed the Roman Greek astronomy so well and really congratulated the Greek and the Romans for the excellent progress they have made in astronomy. So this was the kind of culture that he had maintained. And why he was talking of aerosols, there is a background. 5th century BC, there was a seer called Kanada, very well postulated the Paramanu concept. First definition of an atom, like Democritus Atomos in Greece, contemporary of that era. In fact, our BISC's Sindhi translation as Bhaba Paramanu Anusandhan Kendra also owes its name to Kanada's Paramanu, same word is used. And Varamihira, the Anusiddhanta was not accepted by many theologians of the era, so there were a lot of debates. And Varahamihira was responding to an ancient debate on the size of this Paramanu. So, like when Dalton postulated atoms, questions were immediately about what is the size of that atom. So when electron was postulated, the question was, okay, what is the charge of the fundamental charge? So Millikan did all these experiments to determine the minimum charge. So Varahamira suggested an experiment, an idea, thought experiment to determine the size of the atom. And that is what he says. I have this translation from V. Subramanya Shastri. Incidentally, I came to know his son was a spectroscopist in Bark. I didn't know. I had met this man, but I didn't know he was the son of Subramanya Shastri. And I've even forgotten his name, but I know the person. But this incidentally later I learned. Now, what Varahamira says is this: the smallest particle of dust that comes to sight when the sun passes through the interstices of a window is to be known as an atom. And this is the smallest unit of all measures. And look at the second one. An atom, a dust particle, a hair strip, a nit, a louse, a barleycorn, and a digit are in the order 8 times bigger than the preceding measure. One digit becomes an integer. And since I did not understand the last one digit becoming an integer, I took barleycorn as an estimate of the size. And there are 3 takeaways in these ancient thinkers, which connects to aerosol science. One of them, the dust is a size continuation of an atom he had, and also that the smallest thing can be measured by the least effect, exactly like the Millikan's experiment where he found the smallest charge he measured was electron. So that is the fundamental charge. So he had that kind of a thinking. And his smallest size, of course, it is wrong. He's off by, it is not, he was not really mentioning an atom, although he meant it. But if you look at by light scattering method, it's about 150 nanometers. If you take barleycorn as 5 mm, this is coincidentally the lower limit of radius in today's laser particle counters, which 3.3 micrometer is the limit of all laser particle counters today. It is amazing. It's obviously a coincidence, but very interesting matching. And of course, he also meant in this that the intensity of scattered light is proportional to size. Mayya theory tells it is dp squared. And more interestingly, he uses the logarithmic binning, geometrical binning factor of 8. So we use a 10 today, and all size distributions are in the log scale. Every student is made to know that. So this is, of course, historical. I'm sure this is unintentionally we discovered. If you look at the history of all ancient civilizations, one should do that and collect a history where aerosol related information could come, like in the ancient Chinese civilization, West Asian civilization, and the Western civilization. I'm sure there would be mentioning. And one job of maybe historians or old people like us is to look at how it was in the minds of people. All said and done, we know that aerosol is a subject of the age of reason and age of science. We owe today's aerosol science entirely to the research in Europe and US in the 19th and early 20th century. The term aerosol appears to have been coined by Frederick Donan, if you ask an American, but I have heard Professor Horvath emphatically say that it was August Schmoss in Germany in around the same time. It's very interesting. And aerosol science, of course, became more practical subject after the episode of London smog in 1952, and of course in the US after Los Angeles smog and other events of that time. In the recent times, perhaps no other event has led to the spread of aerosol terminology among public, even into the deep villages of India, than the spread of COVID-19. But it didn't happen on its own. I should really congratulate Lydia Moroska and Donald Milton and the team published in Clinical Infectious Diseases, who made a conscious announcement that it is a time to address the airborne transmission of coronavirus 2019. And if you look at that article, the word aerosol comes at least about 20 to 30 times in that article. Very strongly and emphatically, and without feeling shy, the word aerosol is used. And her second paper is again an announcement. Airborne transmission of SARS-CoV-2, the world should face the reality. It is in fact after this paper by hardcore aerosol scientists that the WHO took note of the aerosol transmission. Until then, we were washing vegetables and not wearing. We are told not to wear masks because there's a shortage of masks. You don't have to wear it. Only if you're infected, you wear. But the whole paradigm changed once aerosol recognition came. So this is the impact of aerosol science in the real world. So this is the power. So what is the science behind it? That's what the aerosol discusses. Of course, today the biggest problem matter is air pollution. I was rather pleased to see this 2 days ago on 8th April that Thailand's city of Chiang Mai was ranked the world's most polluted city on Friday. It was some change. You often hear only Delhi and Indian cities in that. But in any case, the fact is that it's a major issue for us in India, air pollution, particulate pollution. We should emphasize, however, as aerosol people, that particulate matter, whether it is PM 2.5 or PM 10, is essentially an aerosol system. This recognition is not that easy. We, of course, recognize, we don't feel a need to emphasize it. But if you sit in a pollution meeting, control of pollution meeting, you would hardly see the word aerosol ever used. It will be always PM, always PM. Strictly speaking, PM implies any particulate matter, but what is of risk? What is ultimately what deposits in the lung in the form of an aerosol? So word aerosol should be rather, one shouldn't shy away in emphasizing, because by capturing that word, you capture a lot of knowledge and commonality which govern the operational principles of the instruments you're using. The control technology you want to adopt either at the source or in indoor or in various other contexts. And that would, in this recognition that it's actually an aerosol will go a long way in increasing public awareness and in probably addressing the challenges. So we know that this is one of the major drivers of aerosol, should be the major drivers of, or reason d'etre for the progress of aerosol science in India. Let's compare to understand the distinctiveness of your subject. When you say aerosols, questions will come. Is it not a colloid? What's so special about it? It is a colloid, but different. Like I just took up a couple of attributes. A stability. We know that colloids can be stabilized for years. You can artificially stabilize them. You can make them buoyant neutral. You can make them charge neutral. But aerosols, you cannot. It is very unstable, typically hours to days at the most. Typically, unless of course exceptional of stratospheric aerosols, but otherwise it's in hours to days. Transition regime problem is unique to aerosols. In fact, the entire aerosol distinctiveness comes from the fact that there is something called Knudsen number corrections to be applied. We'll speak in some detail about the history of why it is. This does not exist in colloids. I had a lot of discussions with chemical engineers, and they admit that this is a very unique aspect which distinguishes aerosols, which is very significant in aerosols. Then we have Brownian motion. It is important in many places, even in astrophysics, as Chandrasekhar says, but it is limited. But in aerosols, it's too dominant. I will tell you, everywhere without Brownian motion, you cannot understand aerosols, and it is the want of understanding this Brownian motion which often causes guffaw in among many groups who do not understand about the subject. Electrical double layer, so central to colloids, but doesn't exist. Virtually Coulomb repulsions, Coulomb attractions only operate in aerosols. So these are some distinctive features. There are lots of historical reviews. For example, David Ans's historical review is very interesting. Aerosol Science and Technology History and Reviews. It's a relatively recent book. It gives good biographies of well-known people or pioneers in their country, like Otmar Preining in Germany, Sheldon Friedlander in the US, then Uncle Sasha. That is, it surprisingly gives reference to Sutugin's work. That it misses Fuchs, though I didn't see it. Then McLand, Scientific Work and Legacy by Connor. It also runs through several research institutions. So there are so many articles you can see here. I would mention, it even mentions Peter McCurmery, the Minnesota group, for example, Thomas Cohen and David H. Pui. Some of us had, in fact, we had invited, Professor Chandra was instrumental in inviting David H. Pui to IIT Bombay in 2019 for a Golden Jubilee lecture series. He had come. Subsequently, myself and Professor Sahu, we had interacted, and we had actually collaborated on translating their technology of air cleaning in outdoor air cleaners in Delhi, which are set up and going on. And they, of course, they are founders of aerosol filtration technologies. There are many other institutions which are mentioned in this. Then there is the review by G.M. Heidi on atmospheric aerosols, deals with both theory and experiment. There is an excellent review by Richard Flanagan on the history of electrical aerosol measurements, a fascinating review of the subject, how the early measurements of from the lightning days, it has led to the mobility spectrometer of today or control devices of today. So it's an exhaustive review, starting with the Townsend and Zeleny and Nolan, and ending up with Fuchs, Wasner, Gunn, Hoppel and Frick, etc. to modern day SMPS, Liu, BYH Liu, University of Minnesota. Then there is Edward Frederick's works on filtration. It's a very good reviews on filtration by Edward Frederick, as well as K.R. Spurney on the history of air filters. They're very informative. Then, of course, review by Othmar Freining himself and E.J. Davis on the classical era of the 19th century, more like Townsend and others. Now, I will only recount my perspective on the subject. As I mentioned, all subjects are, whenever we look at a subject, it is the famous story of an elephant and 5 blind men. Each one of us has our perspective, and each one, only wisdom is we should not think that that is the only right perspective. Otherwise, it's the same. So this is sort of my perspective. So what are those foundational discoveries which give us that identity and the spirit to work on and an inspiration to drive the subject of aerosol science? A leading journal is always a torchbearer of your discipline, whichever discipline you are in. And for aerosol scientists of the 70s, it was only the Journal of Aerosol Science. Its founding in 70s gave us a sense of unity, whichever country you are. And the spirit of that discipline was very nicely brought out by Norman Davis by this cover. Very interesting. The cover of the Journal of the Aerosol Science of the 70s, then edited by C. and Davis, expounded an inspiring scientific tradition of the subject. It mentions that the journal in the tradition of Einstein, Maxwell, Smoluchowski, Lister, many other names are listed here. So while it is not just ornamental, if you actually look at the subject, these connections are real. The science of aerosols really makes use of all these principles in a very fundamental and very deep way. And that is what I will quickly recount in the next. For example, why do we talk of Einstein? Einstein's work is relevant to every subject. The Brownian movement itself, if you take his 1905 paper in Brownian movement, is one of the 3 papers he wrote that year. It's just incidental. It is important even to derive the black body of radiation of plants, because the alternate derivation comes from Brownian movement. It was observed, it solved the basic issue of when people observed the movement of pollen or movement of some organism, bacteria in water, they were not knowing how to characterize it. Everyone was measuring the mean displacement with time, and they were getting different velocities. Einstein said, don't look at the mean displacement, look at the mean square average of the displacement. That will have a pattern. That will be proportional to time. So the x square equal to 2 dt solved the problem in developed a new dynamics of motion in which randomness eventually has a pattern. Although it's random locally, on a large scale, there is a law, there is a propagation, and that is what it is. So how is it connected? Well, there is a Stokes-Einstein relation which follows this Brownian movement, very fundamental to aerosol science. Mobility equal to d by kt. It's very much true for colloids, more true for aerosols, because you will not be able to have any instrument working unless you know this law. You cannot design it. And then more importantly, you have the whole work of Cunningham, Millikan's, Weber slip correction factor. Millikan's, he started working on electronic charge measurements using charges placed on tiny oil droplets. The first aerosol levitation experiment he did. And there it was required for him to calculate the settling velocity. And he found that it doesn't work for small particles, the Stokes law. So he applied correction factors empirically with some theory. There was not much theory available then, but he did it in a very clever way by using the concept of Knudsen number. And this formula for CC is now a bread and butter for an aerosol scientist. It's a part of teaching. And if you have not heard of Cunningham correction factor, better go and look it up if you want to be an aerosol scientist. And this is the Brownian motion. It went to many other disciplines called random walk and all that. But that is, of course, the branching of the subject. To tell you the importance of Brownian motion in a filtration, I'll give you this example. if you ask why does a HEPA filter capture small aerosol particles, most of the times the answer is not simple. In fact, most people say, even in pollution, people have seen telling that, oh, filters catch only particles above 0.3 microns, but the smaller ones don't have much mass, they are not important. So they pass through, which is not true. Smaller particles are caught with much higher efficiency than some intermediate size. And the reason is given here. If you take that red big particle and a tiny red particle, and if the hole is bigger than the bigger particle, equal hole, the bigger particle will not have much Brownian motion. So it will go straight down along with the flow if you keep it vertically. But the tinier particle, like a wiggly light kid, it will be executing so much of lateral Brownian motion that during the passage, it will contact the surface and necessarily get trapped. So this is the principle of operation of HEPA filtrations. So it directly comes from Einstein's x square equal to 2dt, which can be used for designing how much length, thickness of the bed you need in order to trap fine particles. Another unique curve in aerosols is the famous V curve. Recently, I came across people use the word Greenfield gap or something for this shape, but it was not there in the olden times. But nevertheless, there is always a minimum size at which all functions are minimal, efficiencies mostly, or deposition velocities. The top one, for example, is for electrostatic precipitator filtration efficiency. If you calculate, you will get a minimum like this. And this filtration, every filter has a minimum efficiency around, it varies, but people say around 0.3 micron. So you will have this here. Deposition velocity of indoor aerosol particles, you will have a curve like this, the green curve that you see here. And of course, the famous ICRP lung model has also a minimum of total deposition. So all this comes again from Brownian motion. There are other classical era founders of aerosol discipline. I'll just run through a few names like Lord Kelvin. And without his work on critical nucleus concept, we do not have a definition of the aerosol. In fact, one of the definition is that particles should be larger than the critical size. So that is what his contribution is. Von Marian Smolishevsky. He is the father of the coagulation theory. And aerosol heavily depends on coagulation for long-term modeling, or in aerosol reactor modeling, or smoke modeling, near source modeling, so many other situations. So it's a very important, unique, I don't say unique, it occurs in colloids, but very central to aerosols. Paul Langevin, it was Langevin who first found out that there are large ions with lower mobilities, and they're all because of the attachment of ions to aerosol particles. And that is where the entire charging theory started, and utilization for technology. Gustav Mie. Now, those who work with light scattering in the context of radiative forcing would necessarily know Mie theory. Most people today know about it. And Mie's contribution is so important. He was only trying to apply Maxwell's equation to a two-body systems of a finite size, extending it beyond the Rayleigh scattering theory. But its implication today is so vast and wide. You have, of course, Nikolai Fuchs. Without Nikolai Fuchs, there is no aerosol science. Probably I'll be mentioning it as we go along. Then, of course, Sheldon Friedlander, who established a team of scientists who are now spread over the world, and there is so much camaraderie among them. They're running, editing journals, they're working together. So he's truly I would say, grandfather of today's generation. Then, of course, I mentioned Mandelbrot because I mentioned it at the end. It occurred to me that in my generation, an excitement for us being aerosol scientists, what the fact that the first practical application of Mandelbrot's fractal theory was done on aerosols when Forrest and Witten in 1979 first demonstrated using metal aerosols that look, aggregates have a structure, random aggregates, and they obey fractals. Although he mistook them to be a fractals of so-called classical types, but later studies went further ahead. But today it's a very important method of describing the structure of aggregates which are non-spherical. So these, I would say, in my perspective, are some of the foundational work. Now, electrostatic charging, which I mentioned, I'll give only one example, how that eventually has led to a technology of air cleaning using electrostatic precipitators. You can see the Cortrell's first electrostatic precipitator way back. Of course, many a time technology precedes the science of it. But with the science, the technology becomes designable and scalable, which is what it is today. Similarly, the theoretical contributions in this connection of charging made by people like Roman, Arendt and Kuhlmann, Potenier, White, Nikolai Fuchs, Liu and Ye, more recent, many other recent names like I know Kefe, Nolan and Rich and many other developments, they have finally led to the work of a very precise sizing instrument that is called as the mobility analyzer, the workhorse instrument. But if you look at how it was made possible, it is the so-called classical Boltzmann distribution of charge, which has been derived or criticized, completely criticized today, but the name Boltzmann still hangs on. I'm not going to the details. It should read up the excitement of the debates between Nikolai Fuchs and Kefe, Nolan and Rich, how it was finally new theory by Fuchs has finally solved the problem, but the name Boltzmann has remained. It's very important, the Boltzmann law. But all that is central to the working of this instrument. So this is about the world's history. But if we come back to the Indian aerosol history, it all started in Bhabha Atomic Research Center in the 60s under the visionary leadership of Dr. Homi Bhabha and Dr. K.G. Vora. I'm showing Dr. Mishra here because he took a lot of effort to create the IASTA Forum, Indian Aerosol Science and Technology Association in 1988, which Manish mentioned. He brought together three major institutions at that time, BRC Mumbai, IITM Pune, PRL Ahmedabad. I remember these are the three institutions he brought in. That is Dr. UC Mishra here. Could get some photo of him. And interestingly, the interestingly, the logo you see, you saw it projected earlier also, the IASTA logo itself connotes some physics. It's a Dr. Nair and we discussed it. It was intended to show the picture of a condensing drop in which dust particles are supposed to accumulate. And if it is evaporating, dust particles get cleared by a process known as diffusiophoresis. It was earlier, one logo was used in Journal of Aerosol Science. So we sort of, just to convey that there's a unique process called diffusiophoresis for aerosols, this logo was chosen at that time. The true founder of aerosol science in India is Dr. K.G. Vora, as I mentioned. And as you can see from his obituary, unfortunately, he passed away just a year or two after his retirement. He passed away in 1984, 85. He was loved actually. And he had a lot of friends in Germany. In that time, BARC, we had a lot of relationships, technical relationship with German scientist groups. Othmar Preining was his close friend. And there's a lot of emotion in this obituary that is given. Even cites Tagore. And he says that he's a dedicated teacher, diligently developing experiments for demonstrations in lectures. And the BRC legend has it that Dr. K.G. Vora was actually in an administrative department. He was picked up by Dr. Homi Bhabha to lead atmospheric studies. He was a science graduate, but not initially in a science stream of Bhabha, but he was picked up. He really, he's the father, I would say, from what I know. I don't know about earlier era, whether IISc Bangalore had any groups or Calcutta had some groups, but from all that we know, the aerosol subject, aerosol word started with him. He is also a founding member of the Journal of Aerosol Science, as I mentioned. K.G. Vora, among C.N. Davies, we have Brickard, we have so many names I can't fully read here, but Friedlander is there, T.T. Mercer, so big name, K.T. Whitby, so all names of the leading people of that era. It was started in 1970. It is the first dedicated journal to aerosol topics. Dr. Vora was an associate director in the Division of Radiological Protection, and among other disciplines of radiation physics, he led the team on aerosol specialists. And Dr. UC Mishra was a senior among them. Then there was Dr. C. Rangarajan, Sharada Gopalakrishnan, all atmospheric radioactivity measurements groups. S. Sadashivan, B.S. Negi, Dr. P.V.N. Nair, whom I'm going to discuss later, M.C. Subbaramu, radon specialist Vasudevan, A.M. Mohan Rao, and an instrumentation person called JPS Chatta for trace gas detection. And BARC had the unique speciality that they developed their own instruments. Most of the instruments were developed in the laboratory in those days. There were always very good electronics groups, very good power supply making, so very self-contained laboratory groups. Now, main research of Dr. Vora interest is fallout studies, that is radioactivity in the atmosphere due to atmospheric tests, especially after the megaton bombs, hydrogen bombs came in the late 1950s, tested by America and Russia in the 50s and early 60s. So it was a job to be done. Then he worked at the same time parallelly on radiolytic particle formation, gas to particle conversion, did experiments. Then interaction of radiation and conventional pollutants. There was a fear coming up in those days that if you have a thermal power plant and a nuclear power plant, it is a cocktail of risk, unnecessary, a lot of public apprehensions. But so experiments are the test. So he did experiments of that type. And aerosol thermodynamics with the Dr. P.V.N. Nair, very outstanding contributions of that era. The logic of fallout studies, as I mentioned, was also not only to make measurements of what's going on in the outside world until the partial test ban treaty came, but also the Chinese tests had started at that time. So these measurements of the radioactivity give an idea of the type of fuel used in the weapons. So that was also another purpose which serves. So overall, this kind of studies done over a period of 15 years, they had a lot of benefit, strategic data generation, understanding atmospheric processes, GCM model validations, and residence time estimates. So these continued up to about 60 to 65 or so, and then of course slowly petered out. There were some measurements even in 75, I know, but the main part had stopped at that time. Even trajectory model, which today, like I know, high split type model was done in those ways. You can see that they were able to follow the trajectories. A lot of publications, in fact, nature publications of Vora and Sadashivan, Mishra and Sadashivan came in those days. About radiolytic nuclear formation, his work is basically on gas to particle conversion in a cocktail of radiation and nuclear as well as solar radiations, this kind of studies. And here a lot of publications, Vora Subbaramu, Vora Nair and Muralidharan, etc. And his many papers in IAEA symposia on the behavior of radioactive contaminants in the atmosphere. So these were very formative, I would say, of the what is now becoming increasingly important, the new particle formation topics which are being done. The seed of these studies existed in the studies of Vora. These are the kind of experimental systems, basically glass vessels, some source set up in the laboratory with whatever is available in a research institution. Possibility in BARC, because it was a multidisciplinary institution, you could always get expertise on any area, and very good workshops and laboratory facilities existed. For me, of course, the great thing that Vora did were two big international meetings. The first one was the Indo-German workshop in aerosols in 1978, where almost all the top German scientists, Joachim Haider, Shikarsky, I heard of general dynamics equation, nuclear safety codes then. Nobody was interested in nuclear safety codes, but he was talking about NOVA code in 1978. Werner Stauber on centrifuge theories, Werner Forstendorfer on radon decay product and aerosols, Stalophon on inhalation, aerosolized nebulizer aerosolized inhalation studies, Bunz and all nuclear aerosol people, and J. Gebhardt. First optical counters were being, designed and examined, and that was the period. So all this is abstracted in Journal of Aerosol Science of 1979. I had personally interacted with the Haider. He really inspired me to work on nebulization and examine certain Poisson distributions, whether they're correct or not. So I remember very lively discussions with him. Then another big event was the International Conference on Natural Radiation Environment. It was not necessarily on aerosols. It was a much bigger conference on radiations, but there were very interesting aerosol specialists. One of them I remember is Dr. Holub, who and Dr. Hopke worked on a couple of problems, so I knew. And Dr. Holub at that time was a very exciting person to discuss on the thermodynamics of formation of atomic clusters like radon decay products. Very interesting discussions we have had. And I really remember those I mean, indeed, in fact, opened me to a vast literature on those level of studies in the Journal of Chemical Physics. I now come to Dr. P.V.N. Nair. As I mentioned, he is the aerosol laboratory as well as a thermodynamics person. He's a leading researcher of world repute on atmospheric aerosol thermodynamics. Very quiet, low profile person who don't speak much, but you explore with him. He is a man of a lot of self-doubt. If you speak to him, he'll have lots of caveats and provisos in his talking. Very much interested in the history of aerosols. He's very and had a lot of regard for the German group. He was a good friend of Junge and Junge distribution. He was in Germany for 2 years or so at that time. So very suave, very scholarly person, educated. On all other matters of literature, you could discuss some literature with him. So he's a very educated person. So his major work is binary nucleation. If you look back at his work, he was fundamentally going beyond the classical Gibbsian theory. What we call as Gibbsian theory is basically the first model. Assume Raoult's law, assume simple thermodynamics, generic thermodynamics, but he was getting into specifics. He was doing the thermodynamics of binary nucleation, going beyond the Kohler theory of solutes by incorporating the activity coefficients in those days. And most importantly, he was also doing thermodynamics by including the change in surface tension, change in the material density with the composition of water and sulfuric acid. He introduced the first correction factors by that. So he constructed a lot of graphs like this, which we teach our students today on the equilibrium cluster sizes under various humidities. So he's one of them who extended to sulfuric acid water mixture. In those days, of course, in the mind of people, the question of acid rain was very prominent, and all the studies were motivated to answer those questions of acid rain. Interesting, this I did not know long ago. Dr. P.V.N. Nair was also a technologist. In fact, the first mobile electrostatic precipitator was developed by him for radiation control in thorium plant at that time, indigenously. Unfortunately, we don't even have a photograph of this. BARC doesn't have a culture of photography. It's difficult to take photographs. Then we also, as such, when you come out, the job is done. So it worked. So there is a publication in IAEA document, new approach to the reduction of inhalation dose in working areas using mobile electrostatic precipitators. Just one has this abstract, but I had a conversation with Dr. Nair on this. He said it's a high flow device. It was used in thorium plants. But very interestingly, he told us that Dr. Homi Bhabha was so fascinated by this device that he saw it as a piece of art and arranged to put it up for a display in Jahangir Art Gallery. So he had a lot of friends. Homi Bhabha was a very artist. He's known for his music, his paintings, and love for music. He's a multidimensional personality, and he saw art in science very often. So he had put it in Jahangir Art Gallery. That's what he told me. The most useful, beneficial work for the establishment of a laboratory in aerosol science in BARC was his development of a first continuous particle counter along with the technical person called Marker. It was you can imagine this was a continuous particle nucleus monitor before the origin of today's continuous CPCs, which we buy for 20 lakhs or so. So this was all hand-built instrument. It works on a principle of copious growth of particles above 5 nanometers. They grow to very large supersaturations, then form a fog in a tube. And then it's actually a fog counter. So light attenuated is calibrated against concentration. So total particle count above 5 nanometers it gives. It's quite useful for making an assessment of new particle formation. It's a very simple electronics. And then the whole data is continuously can be recorded in this plotter. This instrument was there up to about the year 2000, and then of course it became dysfunctional, and then new CPCs came, and then the whole thing was discontinued. But another important work that Dr. Nair, in fact, Dr. Nair mentioned that Dr. Marlowe, when he visited India, he was very much interested in this instrument to make a continuous measurements in the US in 1989. Of new particle formations, but some of the project didn't come through. He was seeking fund support for replicating his instrument in the US. It didn't come through. That's what I heard from him. Dr. Nair's another contribution, and of course, Dr. KSV Nambi that time was our leader. although not an aerosol scientist, he gave a lot of support to aerosol research in the then environmental assessment division. One lasting contribution of these leaders were to help us establish what is called as a nuclear aerosol test facility to conduct large-scale, medium-scale aerosol experiments in large chambers. And Dr. Nambi, although it was established much later by us, few years later, but the creative work, the support, and the thing came from Dr. Nambi. Today, that kind of facility is moving out into public domain to IIT Kanpur under the initiative of Dr. Tripathi, who have planning to take it up in a much bigger scale. So this is the kind of vessel under which in which one does aerosol experiments and studies the dynamics. The as I mentioned in the beginning, I was associated with Dr. Payasada Kotrappa. Payasada Kotrappa was a very safe person. This is unfortunately the last photograph, maybe 1980s taken. Very lively he was as a young man, stodgy, pleasing, always a smile. And I worked with him, and we all worked in a fuel reprocessing plant, and our job was to provide radiation protection, no research. But Kotrappa always believed research, publish or perish. You do research, you always your time. So long as the management is kept happy, they will not mind. So fortunately for me, when I joined him, the plant had a refurbishing shutdown of 5 years. He said, we can do a lot of research now. Don't worry, I'll take care of it. So we had very good opportunity to continue research with him. He is the founder. Kotrappa is an inspiring personality because he believed in instrumentation straight away. He did not know much theory. He had a lot of respect for theory though. He had all theoretical. He would give me books on mechanics of aerosols, books by articles by Mercer and all on coagulation and ask, give a lecture on this, read and give a lecture. But very practical, far-sighted. Today, when I look back, he's very far-sighted personality. He was a student of T.T. Mercer at the University of Rochester, and he worked as a postdoc later in Albuquerque. He was fondly called Paul Kotrappa by Mercer, and he majored, as I mentioned, major instrumentation for radiation protection. He left BRC 10 years before retirement in 1985 because he founded a company called Rad-Elec in the US, became a millionaire, in fact, after 86. He developed an electret-based radon monitor to screen houses. That is the time when in the US, radon problem was emerging in the US. He and his collaborator in the US, they built this monitor, and it got US EPA certification as the most reliable house certification monitor. And so he sold a million pieces. He set up a company, it flourished well. And finally, around maybe turn of 2005 or so, he sold his own company and became a scientist there. And he published till the last day. He was publishing papers. And he was a very practical person, man really of the laboratory science. And what were his contributions? First thing is he's the, in those days there were no SMPS. So how do you find the size of smaller particles? So with the light in Albuquerque, he had developed what is called as an aerosol centrifuge. It's an extremely sophisticated device when the particle goes through a channel which is spinning. So because of the centrifugal force, depending on the inertia, different particles get thrown onto a screen or onto a foil at different positions. So then he used to look at color Tyndall spectra and say, oh, 0.1 micron is here. So it's this kind of experience they have had, the shine. It's called Tyndall spectra. So this was built and he reproduced his own instrument in bark, which became a workhorse instrument for us to size particles. A lot of research was done on this. It was used for aerodynamic particle sizing, density, shape factor, production of monodisperse aerosols, etc. How much time do I have?
It is 10, maybe 5 minutes.
Okay, I'll wind it up. Yeah, so most important contribution is mobility spectrometer, which is the forerunner of today's SMPS, built with DUA. And another important contribution is this lung inhalation device, which was used for lung malfunction tests of patients having COPD, so chronic pulmonary obstructive disease. So very this thing. So these were some of his contributions. I have to mention this. Another important contribution is Dinesh Chandrasani. Dinesh Chandra Sahni, if you go to a foreign conference and meet theoreticians, first thing they will ask is about, oh, this is Sahni, the transport theorist. And all aerosol people of some certain era and standing know about him. And he was not an aerosol physicist, far from it. And that is the ingenuity of Fuchs and Sutogin, who discovered him from another subject. Fuchs and Sutogin, who were looking for systematic approach to address transition regime mass transfer in aerosols, they adopted Sahni's solution developed entirely in a different context called the Milne-Black sphere problem. And Sahni is today, of course, he still works and he still publishes. He's happily right now in the UK with his children and grandchildren. A very pleasant person, very confident person, and very precise, as this paper will show. If you look at his original paper, it's a very terse paper, extremely dense. As the scientists of that era, you don't write extra sentence. The maths will tell you. If you know the notations, that's all you should know, and the rest is in maths. So his paper, for example, just ends with this equation, and then a graph, which I'm showing to the left, and says Mayya extrapolation length versus Knudsen number is given here. That's all, the size of the particle, something. So from this content to translate it to an aerosol evaporation problem of a droplets was really an ingenuity that Fuchs had, that Fuchs noticed this paper first. Then he mentions, as he mentioned, is the recent developments on aerosol science are, as he mentions it here, the recent developments are due to Sahni, who was engaged in a research on the theory of transfer of absorption of neutrons, far from the area of anyone working on high dispersed aerosol systems. Then he took his model, he used his plot, gave it a fit, and converted his solution to equivalent of the Sahni solution, extended a formula, which is called today as the Fuchs-Sutogin continuum, non-continuum correction formula. All our students must have used it at some point in time or the other, which simply corrects the transitional flux to the continuum flux via a Knudsen number correction factor. This formula is very popular, as we know, and is my view that this should be referred to as Fuchs-Sutogin-Sahni formula. Of course, the Western world has given so much credit to Sahni. We are not denying that, but still, it demands for the clarity and understanding and the depth that Sahni should be added in this, recognized in this. This is basically the problem. You know, two different formula, and Sahni's formula continuously fits it. And this motivated Sahni. When Dr. Nair told that you have been cited by Fuchs, then Sahni went into aerosols. He developed a new formula for the coagulation coefficient in the transitional regime. This is another alternative to Fuchs transitional regime formula. And he continues doing work on these areas even today and publishes. Very abstract, mostly on problems. So now this is the history, and I really don't want to say much about the future because future should be seen by the people who are there. All that I can say is, yes, this is what we need to do. In a sense of my experience, aerosol knowledge dissemination to stakeholders dealing with air pollution topic is very important, according to me, because that will bring in position. That will bring in, I will tell you an event. There are people who claim air cleaning by using all kinds of ideas, by using radio waves and all that. There is not much expertise to even criticize or make statements. That would come by aerosol community. Then building strong theoretical and numerical groups to attract talent like chemical engineering and mechanical engineering talent to work more on technologies and ideas. Then bioaerosol research is going to be very important. Perhaps much bigger attention has to be given. Pollution control technologies at source, at indoor or outdoor. Capacity building in the area of aerosol synthesis or preparation. Then, of course, in nuclear energy, which is going to be the futuristic clean source. More academic participation should be carried out to enhance public awareness of the safety against aerosol releases. Must tell that it is not really a big worrisome thing. So thank you so much for listening. I am happy to have shared this with you, and it was made possible thanks to the inputs from Dr. Anand and Dr. Manish, and for the help of Ms. Aishwarya with the slides. I thank you all for your kind attention, and the organizers have asked me to just put up this extra slide. So that is for you, and thank you all. Thank you, sir. Thank you. Most inspiring presentation. If there are any questions, we can. Yeah. Chat box. So online participants can type if there is any questions to ask to Professor Mayya. Or at the same time, here offline participants also can, if you have any query or any questions to discuss, yes, you are welcome. Yeah.
So one thing came to my mind, like, so in future, because in this, it feels as if nothing we can't feel about science. So like, you can, like many of your fellow, the people you work with, like Professor Kotaka, he used that he was publishing till his last day. So, I mean, what are your future plans?
What is the question? What?
What are your future plans?
Mine.
Yeah.
To work and work and work. Yeah, basically to educate, to give lectures on aerosol fundamentals as I see it. As I mentioned, it's one profile of an elephant. So there are many profiles, and I look forward to many such lectures on different areas. Professor Chandra can speak a lot on optics, aerosol optics and its implications, which I have not touched because I have not touched anything after 90s. The whole issue of aerosols and climate, aerosols and air pollution, it's all story of the 90s when radar laboratories came in India. In IIT Pune, Dr. Jairam in PRL, Ahmedabad, and many groups in ISRO took over, and Professor Chandra joined. So the story continues, and I'm happy to be around talking to them and pursuing whatever little I can on aerosol research. And I love theory, so whenever somebody says that I need to do some equations, solve problems, I love it. I mean, it's my way of working, realizing the science of it. Yes. Yeah, Mohit. Yeah.
I'm more curious on the bio aerosol community. How people are taking nowadays in India this bio, because European US people are very serious about the bio aerosols. I don't know the status of our country, how they are taking.
So when this announcement of aerosol mode as the transmission was made, since then, all aerosol associations in the world had brought out pamphlets. Probably we are the only country where our decision makers did not even know there existed a discipline called aerosols. Nobody contacted any aerosol scientist. There was no statement from aerosol community. It was, of course, good that many doctors were coming, and of course, they were professional. They were really trying their best to educate. But myself and Anand had discussed, it was a very pessimistic days also. We are all sitting at home and struggling with other things in life, problems. But I have discussed with him to bring out some pamphlet in the name of aerosols. We wrote something, but halfway it was. And I think Professor Chandra was also busy in a world of her own at that time, right, during the pandemic era. So we were all in our own world. But something I feel should not have happened is, it should not happen again. If there is an aerosol problem, aerosol people should speak up. It has to be made aware right at the ministry level that there is a discipline called aerosols for all respiratory diseases, the last word of the propagation, not the science of it, but the physics, dynamics, or whatever of it should come from aerosol scientist. So, and it can come with the laboratory culture. It cannot come with just writing articles.
I wanted to ask this. Yeah.
So yes, it should be established. And
It's heavily lagging. And then now here, it's not being taken up like.
Yeah, I think chemical department, they are interested. Dr. Mahesh is interested. And I think BARC also, they have set up some, they're planning to set up, I understand, on some bioaerosol laboratory. There are youngsters like Sahu, so many, I mean, this is the area to start with the initiating studies. Yeah, so.
Dr. Thank you so much for such a wonderful lecture. Actually, we are waiting to hear this lecture for a long time. So it was a very wonderful lecture. Thank you for that. So, I had a lot of interaction with you. We had a lot of discussion on this aerosol science. A lot of time I have seen people working on the measurement theory and all this. I think ultimately it's a control of the air pollution. If you talk about bioaerosols, particulate matter, all these things have to be controlled. But there are very few people working on control technology. That's why I think I like that slide that a lot of chemical and mechanical engineers should really come into the discipline to come up with new technology, to work with environmental engineers as well, to come up with new technology. So what are your future thoughts on that? Because a lot of people are talking about, without understanding technology, also they are talking about that without a lot of measurement. They have some understanding, fundamental understanding. But without understanding technology, sometimes a lot of people talk a lot of things. So what is your thought on that?
So you see, every science and discipline has its own maturing time. If you look at aerosol science, it was only physicists and chemists. In Bharat, it was dominated by physicists. And I know Mohan Rao telling that, look, aerosol is more chemistry, not just physics, but physics people had the dominance. Although chemistry is so important for effects. But through the environmental engineers came in. It was also, a transition from one set of discipline to another. Then more chemical engineers came in. But still it's not sufficient. I would say many more have to come. So then naturally technology will take a role. So I wouldn't blame anything as a thing, but it finally depends on how much we show interest or how much we promote what is necessary. Awareness is probably very important. But yes, I agree with you. Control technologies have to go hand in hand with diagnostics, monitoring, profiling, and other aspects of pollution. And pollution is a serious subject. It is not just pleasure, as I say. You cannot say that we're enjoying it because it's suffering also of people. So,
one more question actually. This is from Dr. Kriparam. Could you please elaborate more on association of radon 222 and trace gases? Their future research. Okay. Yeah. So this question is from Dr. Kriparam. His question is, could you please elaborate more on association of radon and trace gases? The future research, which is almost dying. Just a small contribution from us on airborne transmission. Yeah, why airborne transmission has not been conclusive in case of COVID-19. So these both questions are from Kriparam. The first one is about the radon and trace gas future research.
So radon is an area where I had worked extensively in the 70s. In fact, much of my more than 50% of my work falls in the area of radon. However, after the recognition in the US that now radon is no longer a risk problem, radon research was closed in the US. And everywhere else, the ripple propagates. And in India, radon is really not a risk problem, but it's an important issue for nuclear department to say how much dose. Vinod, I just see you here. So Vinod is here to defend it, more like his activity. So DAE wants to assign doses to people. It's very important to know it. As an aerosol scientist, radon is very important because it is the smallest size. If you want to understand the behavior of nanoparticles, radon progeny is the best it traces. In 1970s and 80s, before this ELPI came for measuring particles by using charge devices, radon progeny could have been used as tracers. It's very easy to count them. Otherwise, aerosol research is very difficult because there's no way to detect. But radon is so easy to detect. Ideas were used that you could use radon tracers for sizing particles. So there is a scope today on radon research by seeing how much you will contribute to understanding pollution. I've been often telling radon people that if you can measure the unattached decay products in the atmosphere 1 year average, it gives an indication of the annual PM concentration in the atmosphere. Long-term integrating devices, it can help you for long-term exposure assessment. Radon can be supplementary trace things, can be researched like that. So not as a risk item, but as a technology or applicational item for future sciences. That's what I suggest. I think that's, and about COVID-19, well, I think it is now recognized without doubt that aerosol transmission at least is a major component. It's not a unique or complete, but significant component. And that's why all of us wear masks in places where you are well and your friend also is well, but still we wear masks. So that is the logic, I suppose. Yeah. Okay. Thank you, everyone. We'll move to that last part of this lecture series. That is a customary vote of thanks. Good evening, everyone. It's my honor and privilege. No, sir. It's my honor and privilege to extend vote of thanks on behalf of IASTA. First and foremost, we extend our sincere gratitude to Professor Mayya for delivering this wonderful lecture. Also for with our immediate request, he has accepted, and within a short period of time, he has delivered this nice lecture. And in fact, I would like to highlight actually during the executive committee member meeting, everybody's mind, Professor Mayya's name came up immediately for this inaugural lecture. And this shows his pioneering work in this field and association with all this aerosol community in India and abroad. And some people ask, what are you going to do, like Dr. Sani? In fact, as he mentioned during the pandemic, just across a telephonic conversation, he mentioned that 79, he mentioned a work about the Poisson distribution. He said when you atomize a solution, the same concentration you will not get in the droplet, airborne droplet. In fact, that work, theoretical work was attempted and shown that all the aerosol droplets or particles during the pandemic, which is emitted, will not contain equal concentration across the sites, which is a good work, I think, probably is highly cited in the scientific reports. So I think I say it's a knowledge mine. I think we can start exploring in many areas, and that's what IIT and the BRC benefits from him actually. And next, I thank Professor Chandra Venkatraman for immediately giving us this support to conduct this hybrid lecture in this hall, and all her staff, Ms. Manu Bandari, Ganesh, and all other staff members. Thank you for extending your help. And I'd like to thank this IASTA executive members, President Tripathi, Vice President Neeraj, for initiating and organizing this lecture series. Also, we would like to thank all the offline participants here from IIT Bombay and from BRC, Dr. Vinod Kumar, and other senior colleagues. Also, we thank all these online participants. There was overwhelming response, almost more than 200 registered, and many might have participated during this lecture series. And finally, yes, we also thank TSI and Alphatech for the support for conducting this event. And finally, I apologize if I have missed anyone of anyone's name during this process. Thank you very much. And we will end with this vote of thanks, and also a great applause to Professor Mayya for delivering. Thank you. Online participants, you can leave. And